All right, today's lesson is 3.4 chemical equations. So during a chemical reaction, we've talked about this before, what observations you may see. There might be colors changing, bubbles appearing, precipitates forming. Recall precipitates are solids that form during a chemical reaction. You may also detect odors being given off, energy being released in the form of light or heat. But what happens to the masses of the reactants and the products during a chemical reaction? So that brings us to the law of conservation of mass. So Antoine Lavoisier, 1743 to 1794, he was a French chemist, and what he did was he did these experiments where he placed a carefully measured mass of solid mercury 2 oxide into a sealed flask. So very important is that it was a sealed flask. It wasn't open. And then when he heated it, the compound produced liquid mercury and oxygen gas. And when this chemical reaction finished, he found that the measured mass of the products was identical to the mass of the reactants. So he had 10 grams, for example, if he had 10 grams of solid mercury 2 oxide, and then he heated it in that sealed flask, he formed, or what was formed as products was 0.7 grams of oxygen gas and 9.3 grams of liquid mercury. So add those up together, it equals to 10 grams. All right, and that is the law of conservation of mass. And that also applies to atoms as well. And we'll get into that when we look at balancing chemical equations. So that was the law of conservation of mass, which is in a chemical reaction, matter is not created or destroyed. If you start a reaction with 10 grams of reactant, you're going to end up with 10 grams of products. And that's the law of conservation of mass. So when we write chemical equations, we're using atoms. And so we're using chemical equations with their chemical formulas. We don't usually use our word equations when we're looking at chemical equations. And the reason being is because we need to know the exact quantities of chemicals to use when chemical reactions are used in technological processes. And basically, word equations, they're not stating the quantities of the substances needed. And so if you look here at the example, if we say vinegar plus baking soda produces sodium acetate plus water plus carbon dioxide gas, we're not seeing the types of atoms that are involved. So that's why word equations don't work when we're looking at these balanced chemical equations. All right, when the chemical formulas are used, however, so for example, for vinegar, it's CH3COOH, it's aqueous, plus baking soda, which is NaHCO3, it's a solid. It produces sodium acetate, which is NaC2H3O2, it's a liquid, plus water, which is H2O, liquid, plus carbon dioxide gas, which is CO2 with the subscript G representing gas. Okay, when it's written this way with chemical formulas of the reactants and products, then we can determine exactly what atoms are there, what atoms are making up the reactants and the products. All right, so when we look at equations, they are balanced. So a balanced chemical equation has the same elements and the same number of atoms of each element on both sides of the equation. So look here at this example. We're going to go through this example, which is carbon, the C, plus oxygen, which is O2. It's going to produce carbon dioxide gas, so CO2. So looking at this equation, we're going to go through 5 steps to determine, is this equation balanced? So first step, what elements are on the reactant side? So looking on our reactant side, on the left side of the arrow, we have a carbon and we have oxygen. So C represents carbon and O represents oxygen. Next step, step 2, is how many atoms of each element are on the reactant side. So C, there's no subscript, so that means there's one atom of carbon. Oxygen has a subscript of 2, that means there are 2 atoms of oxygen. All right, step 3, what elements are on the product side? Same atoms, there's C and O. C represents carbon and O represents oxygen. Next step, step 4, how many atoms of each element are on the product side? So again, carbon, there's no subscript, so that means there's only one atom of carbon, and O has a subscript of 2, that means there are 2 atoms of oxygen. So last step, step 5, we have to compare our reaction side and our product side and see if they're balanced. So on our reactant side, there's 1 atom of carbon, 2 atoms of oxygen, and on our product side, there's also 1 atom of carbon and 2 atoms of oxygen. So therefore, yes, this equation is balanced. Our next example, we are looking at this example. We have FeO, which is iron oxide, and it's producing iron, which is Fe, and oxygen. So we'll start with our steps again. So step 1, what elements are on the reactant side? So on the left-hand side of the arrow, we have Fe. Fe represents iron, and O represents oxygen. Step 2, how many atoms of each element are on the reactant side? So there's no subscripts, so that means there's 1 atom of iron and 1 atom of oxygen on the reactant side. Step 3, what elements are on the product side? So we're going to go to the right-hand side of our arrow. So we have Fe, which is iron, and O represents oxygen. Step 4, how many atoms of each element are on the product side? So Fe, there is no subscript, so that means there's 1 iron, and oxygen has a subscript of 2. That means there are 2 atoms of oxygen. So now we're going to compare the reactant side and the product side. So our reactant side, there's 1 atom of iron. Our product side, there's 1 atom of iron. Our reactant side, there's 1 atom of oxygen, and on the product side, there's 2 atoms of oxygen. So therefore, no, this equation is not balanced. Reason being, there's more oxygen atoms on the product side compared to the reactant side. All right, so that previous example we looked at, this one here, the equation was not balanced because there were more oxygen atoms on the right-hand side compared to the reactant side. So how would a reaction be balanced? We use these numbers in front of compounds or elements, and those numbers are called coefficients. So there are numbers that we place in front of the chemical formulas, and they are used to balance individual atoms. So if we look at this example of water electrolysis, where basically it's a decomposition reaction, we're taking water and it's a decomposition reaction, so the products are oxygen and hydrogen. All right, so that's a simple decomposition reaction, but the equation would not be balanced if not for these coefficients that were placed in front here of the water and in front of the hydrogen. So those are called coefficients. So what we're going to do is we're going to use this example of the electrolysis of water, and we're going to go through each step to show how this would become balanced. So what elements are on the reactant side? So we have H and O. H represents hydrogen, O represents oxygen. How many atoms? of each element are on the reactant side. So on this side, H2 means H plus H, and there's 2 of these because of the coefficient of 2. So therefore, it's H plus H plus H plus H, which gives us 4 hydrogen atoms. All right, the other way you can do that is multiply the coefficient with the subscript. So 2 times 2, which gives me 4. So 4 hydrogen atoms. Oxygen, same method. There's 2 oxygen, it's O plus O. So there's 2 oxygen atoms. Again, you can just multiply the 2 with a subscript of 1. So oxygen would have a subscript of 1, but we don't show that subscript. But 2 times 1, there's 2 oxygen atoms. So that's how many atoms are on the reactant side. Now let's look at the step 3. What elements are on the product side? It's still O and H. H is hydrogen, O is oxygen. Now we're going to count the number of atoms on the product side. So O has a subscript of 2. That means there's 2 oxygen atoms. Hydrogen has a subscript of 2 and a coefficient of 2. That means there's 4 hydrogen atoms. So again, you can multiply 2 times 2, which gives me the 4 hydrogen atoms. And the last step is the equation balanced? So on the reactant side, there's 2 oxygen atoms. On the product side, there's also 2 oxygen atoms. On the reactant side, there's 4 hydrogen atoms. On the product side, there's also 4 hydrogen atoms. So therefore, this equation is balanced. Okay, so we're looking at this next example here. We have 2 Mg plus O2 produces 2 MgO. We have to check if it's balanced. Okay, so step 1, what are the elements? On the reactant side, we have Mg, which is magnesium, and we have O, which is oxygen. Step 2, how many? We have to count them. So Mg has a coefficient of 2, so that means there's 2 magnesiums, and then oxygen has a subscript of 2, that means there's 2 oxygens. All right, so 2 magnesiums and 2 oxygens on the reactant side. Product side, what elements are there? Mg and O, so magnesium and oxygen. Step 4, we have to count how many of each. There's a subscript of 2 here, not a subscript, a coefficient. Coefficient of 2, so there's 2 magnesiums, but there's also 2 oxygens because this coefficient of 2 is in front of the whole formula. All right, so 2 magnesiums, 2 oxygens. So last step, is it balanced? Magnesium, there's 2 on the reactant side, 2 on the product side. And oxygen, there's 2 on the reactant side and 2 on the product side. So yes, this equation is balanced. All right, let's take a look at our next example. We have Al plus I is producing ALI3. And we also see coefficients here of 2, a coefficient of 3, a coefficient of 2. So first step, what elements are on the reactant side? So Al represents aluminum and I represents iodine. Next, step 2, we have to count how many. So there's 2 aluminums on the reactant side and there's 3 iodines with a subscript of 2. So it's I2 plus I2 plus I2. And if you count that out, there's 6 iodine atoms. So you can count them out or you can multiply 3 times 2. So 3 times 2 gives me 6. On the product side, there is also aluminum and iodine. Now we have to count the number of atoms on the product side. So it's 2 aluminums. There's no subscript for aluminum, so there's just 2 aluminums. I has a subscript of 3, so it's 2 times 3, which is 6 iodine atoms. All right, and our last step then is to just compare the reactant side and the product side. So there's 2 aluminums on the reactant side, and there are 2 aluminums on the product side. So aluminum is balanced. Iodine, there's 6 iodine on the reactant side and 6 iodines on the product side. All right, so yes, the equation is balanced. All right, I think this is our last, yes, this is our last example. So we have CH4, it's a methane gas, plus oxygen is producing carbon dioxide and water. So on our reactant side, we have carbon for C, H is hydrogen, and we have O for oxygen. All right, so those are the elements. Now we have to count our atoms. So on the reactant side, there is 1 carbon. There's no subscript, so there's 1 carbon. And the H has a subscript of 4, so there's 4 hydrogens. And oxygens, it's 2 times the 2, so there's 4 oxygen atoms on the reactant side. Product side, we still have a C, O, and H, representing carbon, oxygen, and hydrogen. Next, we have to count our atoms. So carbon, there's only 1, okay, because there's no subscript, there's 1 carbon atom. Oxygen, there is 2 here with carbon dioxide, so there's 2 oxygen atoms here, but there's also another 2 here in the water. So therefore, there's a total of 4 oxygen atoms, a total. And next, let's look at hydrogen. Hydrogen, there's a coefficient of 2 and a subscript of 2, so that means there's 4 hydrogen atoms. All right, so that's our total. And we just have to now, step 5 is compare the reactant side and the product side. So reactant side, there's 1 carbon. Product side, there's 1 carbon. Reactant side, there's 4 oxygens. Product side, we also have 4 oxygens. Reactant side, there's 4 hydrogens, and product side, we also have 4 hydrogens. So yes, it is balanced.